Hi everybody, let's do the final exam solution for electronics packaging system. That's for senior students elective course. The first semester 2025. The first one's let's describe our level of packaging. Three of them. Okay, as you know that we have three levels of packaging. The first level, that's the ship carriers. The second level, that's the PCB or printed circuit board. And the third level, that's the main board, cables, slot, etc. Now for the problem number 2, you have a microstrip line with the width and the conductor thickness and the dielectric thickness, that's H. And this one actually is the PCB, and epsilon r is given, that's the for glass epoxy, epsilon r equal to 4.7. Okay, ask you to find the characteristic impedance or Z0 of the microstrip line. Ask you to find the distributed parameters L prime and C prime, and then 4.3 the signal velocity in the transmission line, and 4.4 that's the lambda when the frequency is given is 10 gigahertz. Okay, let's get started. Let me blow this up. For the microstrip line, for the thickness is 1 ounce per feet square, that's equal to 1.4 mil, and you know that mil equal to 1/1000 inch. By applying the equation Z0, that's for 4.1, equal to this equation, we just plug in the number. You don't need to convert the unit of mil into any unit, since the unit will cancel out. Okay, as you can see here, H and W and T, they are all in mil unit. So you just plug in the number, you end up with Z0 equal to 79.39 ohms. Now for 4.2, L prime and C prime, that's the distributed parameters of the transmission line. You take a look at the figure 3.2. When you apply the line width, or W equal to 10 mil, and dielectric thickness H equal to 15 mil, you go back to the figure that's given in the final exam paper. Okay, here as you can see, you have the line width 10 mil, right? And with the dielectric thickness H 15 mil, or 0.015 inch, and that's approximately is about 22, and you know the unit is the picofarad per feet. That's your C prime. Okay, so you have C prime is about approximately about like 22 picofarad per feet, and from the relation, your characteristic impedance Z0 equal to square root L prime over C prime, and you can work this out. L prime simply equal to Z0 square C prime. Just plug in the number, and you end up with your L prime equal to 1.39 10 to the negative 7th Henry per feet, or 0.139 microhenry per feet. Okay, so you already have both C prime and L prime. 4.3 signal velocity, and you know that the signal velocity related to L prime and C prime by this equation. You end up with the signal velocity is the 5.72 10 to the 8th feet per second. 4.4 with the frequency is 10 gigahertz. That's the 10 to the 9th hertz. From the relation C equal to F lambda, so your lambda is simply equal to C over F. You end up with lambda equal to 5.72 10 to the negative 2 feet. That's very straightforward for the problem. Next, number 3. Okay, this is talking about our surface resistance and the surface resistivity. It's given the surface resistivity equal to 10 to the 5th ohms per square, and by applying the voltage across two conductors, you will have the current flowing from the higher voltage to the lower one, and this is the dimension of your surface, and this is also a straightforward problem. You simply convert, this one have to be the same unit, because this one is 2 inch and this one is 10 mil. Ask you to look for the current flowing through the surface of the material. Okay, let me blow this up. For your S equal to 10 to the 5th ohms per square, for the square you can do both in the unit of mil square or inch square. For this case, I'm work on the unit of inch square. Your surface resistivity is simply equal to the resistance in the unit of ohms per area, and then by applying Ohm's law, you can find the current equal to V over R. So you need to look for resistance, or R, that's equal to the surface resistivity multiplied by the area. This one is the unit of inch square. So the area of the surface equal to 2 inch multiplied by 10 mil, and you convert mil into inch. 1 mil equal to 1 over 1000 inch, and then that you end up with the resistance equal to 2 by 10 to the cube, and you end up with the current equal to 5 milliamp. Okay. Next, problem number 4. This one is about a transmission line. You have the load N connected to a capacitor, 20 picofarad, and you have the supply voltage 30 volt, and you have the source voltage 100 ohms, and the characteristic impedance of the transmission line is 50 ohms. Ask you to look for the forward voltage VF, the forward current, that's IF, also the backward voltage, that's VB, and the backward current is IB. You already have everything in book and from my lecture, so you just like work this one out straightforward again. I'm not sure this one is missing or not, doesn't matter. Okay. Yep. Oh, okay, this is right here. Well, the first you need to look for the forward voltage VF. You do the voltage divider. By the time the switch is on, uh, the signal hasn't reached the load end yet, so the source just simply can see only the source resistance and the characteristic uh, resistance. That's Z0. In this case, RS is not equal to Z0, so you need to do the voltage divider. That's the ES multiplied by RS divided by RS plus Z0. You end up with the forward voltage, that's 20 volt. For the forward current, simply you go to VF over Z0, and that's then up with 0.4 amp. Now for your VB, since you have a capacitor connected to the load N, your VB equal to negative VF exponential negative T1 over Z0 C, where C is the capacitance. Okay, you just plug in the number. And also backward current by applying Ohm's law, V equal to IR, so I equal to V over Z0. This is your IB. This is your plot. You start with the voltage feeding into the transmission line, that's 20 volt. Okay, and you see starting charging up from 0 and then reach the maximum voltage, that's the 20 volt. That's the problem number 4. Now number 5 is about our thermal analysis or thermal resistance network. You have IC just right here. Let's take a look at picture. And PCB. It's required that the temperature of your IC is not exceed 300 degrees Celsius, otherwise it doesn't work or it's fail. And the different temperature of a PCB and the room temperature or ambient temperature is the 35 degrees Celsius. Heat dissipation given, thermal resistance given. I asked you to look for the maximum temperature of PCB and maximum room temperature. That's the your IC still working. Okay, this one you have to think a little bit, but what you need to do is just the only equation that you need to apply is only delta T equal to QRT, where Q is the what? Heat dissipation in the unit of watt, and RT is the thermal resistance. They are all given. So you take a look into three cases: IC number 1, IC number 2, and IC number 3. But you need to set up equation. Well, this is your IC and your PCB, and your TAC max, or the maximum temperature of your IC that can operate, is the 300 degrees Celsius. And the difference of PCB temperature and the room temperatures that are equal to 35 degrees Celsius. This is your thermal resistance network. As you define TPCB max and T room max. By applying delta T equal to T21, T2 minus T1 equal to QRT. And you set up the first equation, TPCB minus T room temperature, that's the 35 degrees Celsius. That's given. And then from thermal resistance network, you have the heat dissipation, from the IC. And you take a look at this one. Your TIC minus TPCB, of course, going to equal to QRT, where RT is the thermal resistance of your IC, or silicon in this case. So you already have two equations, and from equation 2, we are looking for TPCB max, right? So your TPCB simply equal to TIC max minus QRT. And with the requirement, the maximum IC temperature cannot exceed 300 degrees Celsius, otherwise cannot operate. So this the TIC max equal to 300 degrees Celsius minus QRT. I left this behind because we will work on a different RT and different Q. Take a look at the IC number 1. That's Q equal to 10 watt and RT equal to 20 degrees Celsius per watt. Okay, you end up with TPCB equal to 100 degrees Celsius, and you want to find the T room maximum, the room temperature maximum, the maximum room temperature. That's the TPCB equal to minus the TPCB minus 35 degrees Celsius. Okay, you apply equation number 1, and you end up with T room equal to 65 degrees Celsius, and you can work out the rest. It's just different heat dissipation Q and different thermal resistance RT. Okay, the last one is take a look at the thermal resistance network. We have both thermal resistance connected both in series and in parallel. You have the room temperature T0 equal to 20 degrees Celsius. Ask you to find T1, T2, and T3. That's the junction temperature. And also the heat dissipation, or Q1, Q2, Q3. And RT1 through RT5 are given. Well, this one it's just working. Think about just like equivalent to electrical circuit. So you just let me blow this up. Sorry. Okay. It just work like electrical circuit. Let's take a look at the thermal resistance in parallel. That's your R total. You can find your RT total. That's the 1 over RT total equal to 1 over RT2 minus 1 plus 1 over RT3 plus 1 over RT4. And you end up with RT total equal to 5.71 degrees Celsius per watt. And now your thermal resistance network are in series arrangement. Let's look for T3, T2, and T1 by applying delta T equal to QRT. You pick up this one. Look for that's the heat dissipation flowing across RT5. So you have RTT3 minus RTT0 equal to QRT5. Okay, and you have that's the room temperature T0 equal to 20 degrees Celsius, and for IC1 the heat dissipation is 20 watt, and thermal resistance is 10 degrees Celsius per watt. You end up with T3 equal to 220 degrees Celsius. You do the same thing the heat dissipation flow across the T total. Okay, you already have a RT total, that's the 5.71. I just plug in the number. You do the same thing across RT1, so you have our T1 equal to or T2 plus QRT1. Okay, that's all. Now the last one, I ask you to look for Q1, Q2, Q3, the heat flowing through RT2, RT3, RT4. Same as the electrical circuit. So you have delta T equal to QRT. For Q1, for Q, that's equal to delta T over RT, and different temperature equivalent to the different voltage as in the electrical circuit. So you have T2 minus T1, that's T2 equal to what? This is your T2, 334.2 degrees Celsius. And what is your T3? This is 220 degrees Celsius. Okay, so that's give you 114.2 over RT. Now for the Q1, you have a 114.4 divided by RT2. Sorry, I didn't put like underline here. RT2, that's given equal to 10 degrees Celsius per watt. You end up with Q1, the heat flowing through RT2, 11.42 watt. RQ2 equal to 114.2 over RT3. That's the RT3 equal to 20 degrees Celsius per watt. Okay, and so on. That's the final exam solution for electronic packaging system. Okay, bye.